Hello, this is the lesson that I label lesson 4.3. Not really sure why I number these exactly, just for my own convenience, I guess. But we're continuing on with our study of probability. And today we're going to look at two different kinds of diagrams. One kind is called a Venn diagram. And you might have seen these in other contexts, even in English class sometimes. I think they use it for like compare and contrast sorts of situations. Another kind of diagram we're going to look at today is called a tree diagram. There are 4 probability formulas that you need to know in total, and 2 of them we are going to focus on in this unit, and 2 of them are going to be focused on during Unit 5. And so you might say, why are you telling us all 4 right now? Well, it is because as a student, I always disliked when a teacher would tell me part of the truth and then later on would like add to that or say, oh, there's an exception or something like that. So I'm just telling you everything now, and then we're going to focus on 2 of them this unit, 2 of them next unit. Some vocabulary that you will encounter in this lesson includes a term called independent events and also the term mutually exclusive events. I will caution you that students sometimes think these 2 terms mean the same thing, and they definitely do not. Right, so you either might have the notes printed out in front of you, or you might just be writing your own notes. Either way is fine. I would encourage you to write if writing helps you to learn. If writing does not help you to learn and you would prefer just to listen, that is your choice. All right, so to start out, we're going to think about Venn diagrams. So a Venn diagram is made up of circles, and you might see it as a picture like this, where there's like a rectangle on the outside part, and then there's some circles inside. That's kind of the classic picture. It could also be like this, where there's one group and then there's another group that's a subset of that. So it might be like group A and group B overlap. It might be group A and then group B is a subset of it. It might be, I really didn't plan on my space very well, sorry about that. It might be group A and group B are completely separate one from another, okay? So Venn diagrams help us to understand how 2 different groups, or even more than 2 different groups, could be many, many different groups. But Venn diagrams help us to understand the relationship between different groupings or different events. And the sample space is what is depicted by that rectangle. So if it is possible for 2 events to both happen, then it would be like that first picture that I had that I just took out because I felt like it was messy. I don't know. Just felt messy to me. Okay, so group A and group B. If they both can happen, right, at the same time, if some outcome satisfies both event A and event B as descriptions, then there's an intersection. So intersection you can think of as being like the overlap. A symbol for it is, sometimes you see this symbol, which is like an upside down U shape. So we could say like A intersect B is this red part right here. And then union is including everything. And the way that that is sometimes written is with like a U, like U for union. And so in my Venn diagram picture, if I wanted to indicate union, I would indicate all of A and all of B, including the overlap part. Literally everything that is in A or in B or even in both. Okay, if you're in some part of A, some part of B, some part of both, you're in the union. So I'm getting a little ahead of myself here because I did include some pictures for you to shade. So I would ask that you just write down these diagrams if you don't have printed notes, and pause the video and try to just color in the parts that pertain to the description. Okay, I want you to try these yourself. So if you need to pause to draw them, do that. And if you already have the drawing, still pause and try, okay? Because I just want you to color in the parts, kind of like what I just did here. Color in the parts that pertain. Okay, pause. All right, so here are solutions. Hopefully you match mine. So set A, you highlight A. Notice that you include the part of A that is in the intersection, okay? So one way to think about this is to think about outlining the set. So set A, its outline is this outline. So everything that is inside of that circle gets colored, even if it's in the overlap. Same idea for B. This one means intersection, so it's just the part that's in the overlap. This symbol means union, so it's everything. Unionized, union all together. All right, the next set of pictures is here. So I, again, would like you to pause and draw these if you're taking your own notes on your own paper. And then in a second, I'm going to ask you to do some more coloring. So the complement refers to the opposite. So we talked about this in one of the earlier videos this week about how you could find the probability of A by taking the opposite, right? Find the probability of not being A and then subtract that from 1 or from 100% if it's in percents. And the little notation that you sometimes see for that is using this tiny little C. So this first question, question 5 on my sheet, says shade the region corresponding to the complement of A. The way that I would think about that is here is set A, and I want the opposite or the complement of that. So that means I want, instead of coloring inside the circle, I want to color outside the circle. So it's like instead of coloring inside the lines, you're coloring outside the lines. Okay, so given that, I'd like you to write down the next 3 questions, pause the video, do your shading, come back and see if you're right. Pause. Okay, so these are doing the complements of the questions that we did on the previous slide. So if you look back, I asked you to do A, B, intersect, union. And here I asked you to do A, B, intersect, union, but the complement. So it should be exactly the opposite of what you did on the previous slide, right? If you look at question 4, this purple shape right here should fit exactly into the space that you left open here. Okay, so that's emphasizing to you how complements are the opposite of whatever you're referencing. All right, so fun drawing. I hope that was fun to you. All right, so now we have a question that doesn't involve any sketching or any shading anyway. It has a picture. It has a Venn diagram. So in this question, it says that there were 80 students who were asked if they take math and if they take history. So if you think about like your survey project right now, you might have questions like this. Do you do this? Do you do that? Right? So they had 80 people in their sample. They asked both of those questions. And then in their Venn diagram, they're showing the relationship in their data. So there's some people in the math group, some people in the history group, there's some people in the overlap, and then there's a 17, whatever that is. So let's try to figure out what's what. So down below, I have some questions for you. If you need to take a second at any point to update your notes, feel free to pause. Okay, so the capital P here means probability. So the probability that a student takes math. Well, there were 80 people who took this survey. And out of those 80, I need to think about who takes math. Now, a common wrong answer right here would be to write 23 out of 80. 23 out of 80 is not the right answer. Can you tell me why? Well, that was a fun conversation we had right there, but you are right. If you think about that highlighting that we just did, if I said highlight the group that means that took math, hopefully you'd highlight all of this circle, just like back here, you highlighted circle A and you included the overlap. So it's the same strategy here, okay? So we'd have 23 and 14. So that's a total of 37. Okay, same idea holds when we look over to the history circle. So for history, I'd want to include everyone in this history circle. So if we add that together, let's see, that's 40 out of 80, which is 50% or a half. If you want to reduce, you don't have to. The next question says find the probability that a student takes both, takes history and math. Well, that and indicates I'm looking here at this overlap region. That's what I want to look at. Those are the 14 people who take both. So that's 14 out of 80. Now the next part is a little bit strange because the way that English works is not quite the same way as how math works. So when we say math or history in day-to-day speech, we might mean only math and only history. That is not what we mean in probability life. We mean I am a person who takes math or history or both. In other words, or is a word that means union. Ooh, that would be good to write down. I'm going to write that down. So, or, I want to think union. And in the previous question, I wanted to think about the overlap. That's good, or the intersection. Okay, that's maybe helpful. Okay, so a student takes math or history. That means these people who take just math. It also means these 14 people who take both. It also means these 26 people who just take history. So that's a little different, right, from how we would normally think about the word or. So that would leave us with 23 plus 14 plus 26. That's 63. Oy. Right, so the one number that didn't get used in this problem yet is the 17. What's true of the 17? The 17 people don't take math and they don't take history. They take neither one. So no math, no history. They are outside of those two groups. Right, so we're now up to the part where we're going to define one of the two terms that I said people get confused, right? So the word independent events means that if I have two events, A and B, and I say these two events are independent, whether or not A happens has no bearing on the probability that B occurs. So if two events are independent, then the probability that they both occur, you can just find by multiplying them. Okay, so here I'm going to write this out. If A and B are independent, then it has to be true that the probability of both them happening is the probability of event A happening times the probability of event B happening. All right, so to use this idea, one use of this is to test and see if certain things are independent or not. So for example, we had this nice Venn diagram from our data, and I might be curious, are the events of taking math and taking history, are those independent or not? Well, I can use this as a test. Okay, so if math and history, I just abbreviated those. If math and history are independent, then this formula over here would have to be true for my two events. So the probability of math and history would have to be equal to the probability of math times the probability of history. Now, I have no idea if this is true or not because I don't know if these are actually independent events or not. But we just found all of these probabilities. So in the last question, the probability of math and history, that was those 14 folks out of the 80. The probability of taking math, there were 37 people out of 80. And the probability of taking history, there were 40 out of 80. So I need to see if this is a true equation or not. So I'd get out my calculator, and this fraction is 0.175. This fraction times this fraction gave me the decimal point 23125. Those two numbers, they are not the same. So what can I conclude? Well, since this equation wasn't true, then this statement cannot be true either. So I would say, therefore, math and history are not independent. Which, guess what that is called? You're right, dependent. Not independent means dependent. Okay, awesome job. All right, so this is a way that things get used, like that definition gets used as a test to see if events are independent or not. Okay, so the other term that people sometimes think means the same as independent, but it just isn't. It's not. I understand why people think this, and maybe you'll be in that camp too. I hope not. But it is a very different idea. So the idea is what is called mutually exclusive. Another word for mutually exclusive is the word disjoint. And so I use those both interchangeably. I probably should just pick one, but old habits, you guys. It's been decades, okay? So I use both of those words interchangeably, both of those terms. So if two events are mutually exclusive, it means that those two events actually literally cannot both happen. So another word for mutually exclusive, as I just mentioned, is the word disjoint. I'm trying to highlight that, but it is not happening. Okay, there we go. So another word for that is disjoint. And if A and B are mutually exclusive, that means that their probability together, both of them happening, is 0. Because the way that that would look in a Venn diagram is like this. Here's event A, here's event B. There's no overlap because it's impossible for both of them to happen, right? Because they are disjoint or mutually exclusive. Okay, so that's what it looks like when you have mutually exclusive events. It's like I have a deck of cards, I'm going to draw a card. What is the probability that I draw a card that is a queen and a 4? I can't draw one card that is both a queen and a 4. It's impossible. Now, could I draw a card that is a queen and a heart? Sure. There's definitely a card in the deck that is both a queen and a heart. So those two groups, queens and hearts, they overlap. Queens and 4s, they don't overlap. It's impossible to have something that's both. Okay, so my big note, these two things, independent events, mutually exclusive events, not the same. You can see it in the math, okay? So the math we just were looking at is how probability of A and B both happening is 0, impossible, if my events A and B are mutually exclusive. However, if my events A and B are independent, I have a formula. It's not equal to 0. It's the probability of A times the probability of B, right? If I multiply these together and I have that formula, then my events A and B are independent. Okay, so you have a whole different formula. These are not the same terms. All right, I mentioned in the introduction that there are going to be 4 formulas. You just saw one of them a second ago. We saw this one. We used it to check if math and history were independent events, which they were not. Okay, and this equation I referenced in a video lesson earlier this week. I said that the word or, unlike in the rest of the world, is going to indicate adding, which is super weird because usually adding goes with the word and in probability life, and goes with multiplying. So weird, okay? So the 2 formulas that I circled on the screen right now, those are the 2 that we're going to focus on in this unit. Now, there are other formulas that kind of are similar, but a little different. And so I just want to give you the heads up because I really hated this as a student. So there's a different formula for and there's a different formula for or. And those 2 are going to come up in Unit 5, okay? But for now, really just hang your hat on knowing the 2 that I circled, knowing the fact that the and formula, you have to have independent events. And knowing that for the or formula, you have to have mutually exclusive events. Okay, that's what you have to know for now. All right, the last thing we're going to talk about today is another kind of diagram, which is called a tree diagram. Now, there can be times when it's really not clear to us in the problem if we have independent events or not. And especially in those situations, it can be helpful to just draw out a diagram of what's going on, and we can figure out the probability from that diagram. So for instance, let's say that we are going off to soccer practice, and in soccer, love being the goalkeeper, okay? So it really depends, like the likelihood of that happening depends on who's coaching today, because the coaches have different feelings about our goalkeeping ability. So with Coach Sam, you've kind of kept track over time, and it turns out that if Coach Sam is coaching, that means that you probably have a 50% shot at being goalkeeper. Coach Alex doesn't believe in your goalkeeping ability quite as much. And so then your probability of being goalkeeper is about 30%. But it's also the case that they aren't coaches the same amount. Sam is more frequently the person who's coaching the game, and Alex is a little less frequent the coach for the game. We want to know the overall probability that we get to be goalkeeper today. So I'm not sure if these are interrelated or not. It doesn't say independent, it doesn't say dependent. I'm really not quite so confident, but I'm confident that I can make a tree diagram of what's happening. So there are basically two things that have to happen. We have to figure out who's coaching, and then given who's coaching, we have to figure out the likelihood of being a goalie. Okay, so the two coaches are Sam and Alex. So you see, I start out here with a pair of branches because there are two options. If there were three different coaches, I'd have three branches, okay? And then this set of branches, this tier, okay? So what I'm seeing right here is like this as a tier of my picture. That tier represents the decision of coach, right? Then there's going to be another tier of branches. It's going to again have two outcomes from each entry point, and it's a matter of if I get to be goalie or not. Okay, if there were more options, right, like my being goalie or midfieldman or something else, right, if there were like a bunch of different options, I'd have more than two branches, but this is really just a two decision thing, goalie, not goalie, okay? Then in a probability tree, oh, and then I wanted to emphasize, so this tier of branches has to do with the choice of goalie. So the first tier of branches was choice of coach. Second tier of branches was tier of goalie. If there was another decision to be made, I'd have another tier of branches. Okay, now we're going to go through and put in the probabilities. So it says Sam is the coach more often, 60% of the time. So if this is 60%, not Sam is the complement, so that would be 40%. Then over here, if I am now at this part of the diagram with Coach Sam, the probability that I get to be goalie is 50%. So I'm going to say there's a 50% chance of my being goalie, which means there's a 50% chance that I'm not goalie. However, Coach Alex makes different decisions. Coach Alex gives me a 30% chance of being goalkeeper. And if that's 30%, the complement of that is 70%. So here's a nice tidy version of what I just drew. And then you can see over here, what you do is you just multiply. This happens and this happens. The word and in probability life means to multiply. And I can do that for the next branch and for the next set of branches and for the next set of branches. Okay? And then if I multiply that out, I will get the probability of each combination. So this 30% means there's a 30% chance that Sam is the coach and I'm goalie. There's also a 30% chance that Sam is the coach and I'm not the goalie. There's a 12% chance that Alex is the coach and I'm the goalie. And there's a 28% chance that Alex is the coach and I'm not the goalie. Now, my question to you is now, what should these numbers add up to? If you said 1 or 100%, you are correct. And that my overall question in this was, what is the probability of being goalkeeper? Well, let's look at the things that caused me to be goalkeeper. here I'm the goalie because that says yes, or here I'm the goalie because that says yes. Now notice I said or. So either Sam and goalie or Alex and goalie cause me to be the goalie. And or means to add. So this would be my 30%. Actually, let me show it this way. Sam and goalie was 0.6 times 0.5. Notice and meant times. And this was 0.4 times 0.3 and meant times. And this was 0.3 and this was 0.12 for a total of 0.48. So I have a 48% chance of being goalie. Right, this is the closing question that I'd like you to try. I want you to pause the video and then come back in a second to see the answer. Okay, so this is a pretty complicated question, and I want to just say up front, if you figured this out a way other than what I did, but you still got the right answer, which is 3 out of 11, you rock, you're awesome, okay? So the idea here is that you're taking out 3 different balls that are different colored balls from a bag, okay? And so you want to take out a ball, keep it, take out another ball, keep it, take out a third ball, keep it. And the question is to figure out the probability that all 3 balls are different colors. So I did go ahead and draw a big tree diagram, and this just helped me to think about the question more than anything. So if I drew a white ball first, I would not want to draw any other white balls, but I could draw white, then green, then red, or I could draw white and then red and then green. Okay, those would be 2 possibilities that I would like. And so I wrote that down here. White, green, red, white, red, green. Those are 2 possibilities. Then I went to my next section of the tree. So well, if I drew green first, then white, I'd want red because I have to have all 3 colors. Or I could have green, and then I don't want green, maybe red, and then white instead. Okay, and then the same thing comes up down here. If I draw red first, then I don't want red again, but I could have white, and if I have red, white, then the third one has to be green, or red, and then green, and then white. So the tree diagram is what I use to conceive of all of these 6 options. And then I am going to be drawing from this bag. And if you look at this, this has 3 plus 4, which is 7, plus 5 is 12. So the first time I draw, I'm going to have 12 balls that I am selecting from. Then the next time I'll have 11. Then the next time I have 10. So my denominator is going to be 12 times 11 times 10. And so 12 times 11 times 10 is my denominator, which is 1320. And then I just wrote out all of the different possibilities. So this option is here, and this option is here, and so on. Okay, now it turns out every single option has a 3, a 5, and a 4. 3 times 5 times 4 is 60, and there were 6 ways of doing that. So this is how I just did it to sort of shortcut my arithmetic, and that fraction is this last guy. Wow, that is a challenging problem. I'm glad I stayed awake through almost this whole half-hour lesson, for crying out loud. Let's be done with math now, okay? So go ahead, try the problem set, and do the best you can. You guys are doing great. You are rocking out this e-learning business. This is going to pay you dividends in college because I know that you are becoming a more independent learner through all of this. That said, if you are confused, please, please email me and say that you're confused, or come to the next time I have a Google Meet so you can ask me questions, okay? Don't flounder. Talk to you later. Bye.